and we have made it worse by announcing in the morning lectures. So the postdoc talks are supposed to start from 5, not 4:30. Okay, so this talk will last till 3:30, then half an hour tea break, then 1 hour postdoc talk, and then from 6:30 we will have the physics lecture. Two talks. See, I am still getting confused. 2:30 to 3:30 there is one talk, then half an hour break, and then there are... there is one more talk, yeah. See, so many times there are some changes. So there are 2 talks at first, then we'll have 2 more postdocs, and then we'll have a physics talk. No. Postdocs are 25 minutes each. So I hope I have not made it worse. And there are some other announcements. It seems we had some gifts for everybody, like including notebooks, pamphlets, pens. There are many which are still lying around. Maybe some of you have not yet taken it. So I encourage you to just find some volunteers and take it. And the next one is after this talk, there will be a tea. And at that time, we will have some complimentary coffee mug. So please, everybody also take that. Coffee mug. Okay, yeah, over. Right. And as everybody should now know, 2:30 is every day. Lunch is 1.5 hours, 1 to 2:30. And tomorrow there are no afternoon lectures. There will be a reminiscence session, continuing with some panel discussion, and then there will be another physics talk. And similarly, on Friday, we are going to finish it by the lunchtime. That's not yet decided. That's when we will announce tomorrow. And on Friday, we are going to be done by lunchtime. So possibly we might arrange some excursion trip, but you are also encouraged to visit the city and also. So we might. There are institute buses. Yeah. Yeah. No, 2:30. Everything is from 2:30. Yeah. So lunch is from 1 to 2:30 every day. There is no confusion. Okay. Sorry.
Okay. So welcome back to the afternoon session. Now the speaker Milicic from University of Utah, and he will speak on Harishchandra's orthogonality relations.
The topic is a little bit stale because the paper appeared in the press already, but it's related to the work of Harishchandra, and also I think the proof I will sketch for people who were at the workshop is a good illustration of various results discussed there. Says homological induction, D modules, and also Parthasarathis lectures on construction of discrete series characters. So to start, let me briefly review Schur orthogonality relations and Hermann Wald's work on characters of representations of compact groups. So let G0 be a connected compact group, and T0 the maximal torus in G, and let me denote by mu of G0 and mu of T0 normalized R measures on U0 and T0. And let's denote by mg0 the category of finite dimensional representations of G. then of course MG naught is a semi-simple abelian category, and if we, oh, it's not on. Is it on now?
Yeah.
Okay. Okay. So let's see where I was. So if V is a representation, V denoted by bracket V, the corresponding elements of the K group of G naught. And then we can define, as usual, the multiplicity pairing of two representations to be dimension of Hom G from V to V prime, and for any two representations there. Also, if V is a representation of G naught, we can denote by theta V its character, and this character map extends to the K group of G naught, and we can define a pairing given by integration of characters over the group, and by sure orthogonality relations, those two parities agree. So now let's be more specific using structure, the theory of compact Lie groups. Let's denote by G, German G and T, the complexified Lie algebras of G naught and T naught, respectively. Let R be the root system of the pair GT, and W the Weil group of R, and bracket W the order of the Weil group. And for any root alpha, let me define by E alpha the corresponding homomorphism of the torus into a group of complex numbers of absolute value 1. Then we can define this dt as a product over all roots of 1 minus E alpha t. And we have the famous Weil integration formula, which expresses the integral as integral over conjugacy classes, and each conjugacy classes pass through maximal torus, and then we integrate over the torus with this fudge factor dt, what was discussed at least on a geometric side in Raghunathan's lectures. And if we apply this to characters which are constant in conjugacy classes, we get this formula for the pairing. And a classical argument of Hermann Weil to find the characters of irreducible finite dimensional representations use this formula. Harishchandra, as was discussed by in Parthasarathis lectures, tried to mimic Hermann Weil's approach to construct discrete series representations of G naught. And again, I need to introduce some notation. Now, G naught is a connected semi-simple Lie group with finite center. K naught is a maximal compact subgroup of G naught. And T naught is a maximal torus in K. And G, K, and T are complexified Lie algebras of those groups. And I denote by K and T complexification of corresponding groups. And let me denote by AGK the category of Harishchandra modules of finite length. This is an abelian category, but not semi-simple in general. And let me denote by KGK its Grothendieck group. As again was discussed by Parthasarathi. Harishchandra proved the theorem that discrete series exist if and only if the rank of G naught is equal to rank of K naught. So in this case, T naught is a compact Cartan subgroup of G naught. Also, as was discussed in the workshop, for any Harishchandra module, we can denote V, we can denote by theta V its distribution character, which was defined by Harishchandra. And by regularity theorem, it's given by locally integrable function analytic on the regular set, and I'll denote it by the same symbol. And this extends to the homomorphism of the K group of the category. Again, if it denoted by R the root system of the pair GT, and R plus is a set of positive roots, then Harishchandra proved an extension of this statement about analyticity on the regular set, and he proved that on this compact Cartan, actually character extends to multiply by this essentially, while denominator extends to a real analytic function everywhere. And so in this situation, we can define this pairing, which we call elliptic pairing, which is just to integrate those extensions over the torus and divide with the order of W naught, which is the compact Weil group. And I will call this the elliptic pairing on K group of the category of Harishchandra modules. Of course, we can define this in general, but then if the group doesn't have compact Cartan, then we just say that elliptic pairing is 0. So if we consider discrete series, the subcategory of a category of Harishchandra module consisting of square integrable Harishchandra modules of finite length, that this is a semi-simple subcategory, and what Harishchandra proved that the elliptic pairing in this case agrees with multiplicity pairing. So you get the same result as in the case of compact groups. And he used this observation to find formulas for the characters. So when I was at the Institute in 75, 76, Harishchandra, and the year before he proved Plancherel formula, and Schmidt was giving serious lectures on discrete series and the proof of Langland's conjectures. And one of the things he did, he suggested me to study asymptotics of discrete series, so the precise rate of growth of those representations, and we were discussing some related problems related to discrete series, and we were wondering what is the extension of Harishchandra orthogonality relations to arbitrary admissible representations. We didn't go anywhere, and if one looks now at this, it's quite clear why. At that time, the homological algebra of Harishchandra modules was not well understood, except maybe by Greg Zuckerman and David Vaughan, but their results were not available in written form, and I also at that time didn't have a clue about homological algebra. So let me now go back and try to explain how one should look at this problem to get the result more or less by formal arguments. As I said, this elliptic pairing can be defined in all situations, but in the case when rank is not equal, we put the pairing is equal to 0. And to construct the analog of a multiplicity pairing in our approach, we have to, since the categories are not semi-simple, we have to use corresponding derived categories to deal with homological algebra issues.
Your microphone went off.
Oh, really? Oh. Yeah, I think I touched my pockets. Okay. So, I mean, the problem is that home is not exact in this case. So let me introduce a little bit more of notation, but so MGK is a Abelian category of GK modules, so I'm not assuming anything like finite length. It's just G modules, say K modules with compatible actions. DBGK is corresponding bounded derived category of this, and DBADN is the full subcategory of derived category with consisting of complexes with cohomologies, which are Harishchandra modules in previous sense, so which are finite length. Then we have natural functors from the, from the category of GK modules into derived category, which put a module in the complex in degree 0 and all the others 0. And this functor induces a morphism from the category of Harishchandra modules into the core of this triangulated category, DBADN, with respect to natural T structure. Moreover, there is an inverse map which proves that this map is an isomorphism, which if we look at Grothendieck group of the derived category, then we send a complex into its order characteristic, and this defines the inverse map. And in this way, we can identify Grothendieck group of the category of Harishchandra modules to the Grothendieck group of this triangulated category. And now we consider the bifunctor between the opposite derived category and derived category into complexes of vector spaces. This is R home of GK. And we can restrict it to our subcategories of complexes with admissible cohomology, and then by result, I think, due to Vaughan, the complex we get on the right side has finite dimensional cohomology, and of course it's bounded. So we have the following diagram. I mean, from these categories we go into corresponding K groups, and from that we get the category of a K group of finite dimension of vector spaces with finite dimensional cohomology bounded, we can take the Euler characteristics of dimension and we end up in Z. And this map here gives us a pairing on K groups of Harishchandra modules, which we call homological pairing. If, and I will denote it by this formula, and if you calculate it on two Harishchandra modules, then you get that this pairing is given by just alternating a sum of corresponding X groups of the modules. So it's sometimes called Euler-Poincaré pairing. So the main result I want to explain is this theorem by Huang, Sun, and myself, which says that those two pairings are the same. And this generalizes Harishchandra's orthogonality relations to arbitrary Harishchandra modules. Analogous result was conjectured by Kazhdan in case of p-adic groups, and it was proven by Bezrukavnikov and Schneider and Stuhler. Okay, so to explain the proof, which is... Any questions?
It's making noisy speak.
Okay. So, sorry. So now I can't read notes. No, I can read this. I cannot read my written notes. Okay, unfortunately, I have to again list some notation, but fortunately this was notation used in the workshop. So if I denote by sigma Cartan involution corresponding to K naught and G naught, and I pick a sigma stable Cartan subalgebra, then it splits into toroidal and vector parts. So we have this deck C is T plus A, and let's denote by T the subgroup of K which centralizes C, and T is its Lie algebra, and we can look at the corresponding category of CT modules, and clearly corresponding irreducible CT modules are finite dimensional. Therefore, in this case, ACT is the full subcategory of finite dimensional CT modules. So now let's fix a root system of a pair GC and a positive set of roots. It determines some N, which is some positive root subspace, and C plus T determines a Borel. And T normalizes B. And we can first of all define Lie algebra homology of this Harishchandra module V, and it is a CT module. And by abuse of notation, I will denote by H lower bullet N the derived functor of Lie algebra homology from dBGK into dBCT. Now I want to repeat the construction explained in Arvind's lectures in the workshop. First of all, the forgetful functor from MGT into MGK into MGT, as it's well known, is called, has an adjoint gamma KT, which is called Zuckerman functor. And then if I have my fixed Borel, I can look at the space of hom UB, UG into U, which you can consider as formal Taylor series of B, UB invariant maps from U of G of U, or Taylor series of the sections in corresponding vector bundle, and it has a natural T action, and we can consider the largest algebraic submodule of this gadget, on which U of G acts by right multiplication on the U of G here. In this way, one gets a GT module, and by applying Zuckerman functor to this, we get this functor ICR plus, and its derived functors functors of cohomological induction, and both functors have finite cohomological dimension. The derived functors exist, and between corresponding derived categories, and they are adjoint to each other. So we have this form of Frobenius reciprocity. Using the finiteness results I mentioned before, we can, and using previous construction, we can find a multiplicity version of Frobenius reciprocity, that our homological pairing between some V dot and the cohomologically induced module is equal to the pairing between n homology of V and this U dot, which is basically the inducing module in our cohomological induction. So the first observation one does is to show, and this reduces basically using this form of Frobenius reciprocity to using Zool resolution for A for the split part of Cartan. We show that the pairing is trivial if the vector part of the Cartan in cohomologically induced complex is non-zero. So the only case when we get something non-trivial is if A is equal to 0. So this is essentially enough up to various manipulations to prove, as you will see, our statement, except that we have to show that we have enough of this cohomologically induced modules, and one way to see this is to use localization. So D modules, so let me denote by X the flag variety of G. We take a K orbit Q and irreducible K equivariant connection on Q, and let IQ tau be the standard module, the lambda module, what we called actually in the lectures Harishchandra sheaf, standard Harishchandra sheaf, and what was proved there, that any standard Harishchandra sheaf has a unique irreducible subobject, and global sections under certain positivity condition, and this anti-dominance condition, they exhaust irreducible Harishchandra modules. From this it follows immediately that for anti-dominant lambdas, all the K group is generated by global sections of the standard Harishchandra sheaves by their classes, and by applying Harishchandra duality, we can also say that the duals of these modules generate the K group. So now we pick a point in the orbit Q and look at the corresponding Borel subalgebra. Then this Borel subalgebra can be decomposed in C plus N, where C is sigma stable Cartan subalgebra. And let's denote by S the dimension of K intersected with N. And let U be geometric fiber of the connection tau on the orbit Q, consider as a CT module, and let's omega x be sheaf of sections of the canonical bundle on X. And Tx of omega s is geometric fiber. Then the duality theorem of Hecht, Schmidt, Wolf, and myself says that the dual of the global sections of our standard Harishchandra sheaf in this situation are given, is given as this est cohomologically induced module for the data written there, and all the other cohomologically induced modules vanish. So the conclusion is that for a Harishchandra module V, we get the pairing between V and the dual of some global sections of some standard Harishchandra sheaf is equal to 0, of course, if A is non-zero, because it vanished. Homological pairing vanishes there. And in the case when A is equal to 0, then we get the following formula here, that this is equal to -1 to S H bullet and V, the pairing corresponding to T U check Tx omega x, or if you just write down explicitly what this is, you get this formula. There's the sum -1 to S plus P, and pairing between teeth and homology group, and this U check, which appears in our cohomologically induced module. Okay, so now, I mean, our proof consists actually from computation, explicit computation of homological pairing, as you will see. And as I mentioned, if the rank of G naught is bigger than rank of K naught, this pairing is 0, and the theorem is proved there. So what we have to consider is the case of equal rank. And the proof there, at least, is based on Osborn conjecture, proved by Hecht and Schmidt, and we need Osborn conjecture only in the case of compact Cartan. If one looks at Hecht-Schmidt's paper, then one can see that they remark there that actually the proof of Osborn conjecture in that case is contained in the Schmidt's paper, I think, on the proof of Langland's conjecture for discrete series. So basically, Osborn conjecture says the fact which is stated here, that the character on regular elements, say in a compact Cartan, is given as the quotient of this Euler characteristic in Weil denominator. One remark I want to make, that actually our proof can completely avoid the use of Osborn conjecture up to the very end. At the very end, one has to identify expressions like this with characters to connect the homological pairing with the character pairing. So, I mean, at that point, one has to use some analytic information, of course. So now we can try to compute the pairing. And I wrote here a bunch of formulas. I don't think, first, basically they just use some symmetry we have in this case to simplify our original statement. First, I average under the action of compact Weil group, then I switch the order to get the Euler characteristic, and then at the end, I mean, one can reduce this to the formula like this. And the last expression, so this expression here, corresponds to the character of our module, of this module on a compact Cartan, and one proves this by checking which module this is. This is a module of global sections of certain standard Harish-Chandra sheaf, and then there is a connection between a localization and a factor of geometric fibers, which tells you actually how n homology looks at a particular in a particular weights, and this allows us to establish the equality of the previous formula with this formula. So, since, as we remarked, our duals of global sections of standard Harish-Chandra sheaves, they span the K group, it is enough to check the formula on the generators, and we just did this, and this proves this identity, which gives us the homological pairing of two Harishchandra modules in terms of n homology for n's attached to compact Cartan. And this is the formula for n homology we want. And as I said, up to this point, we can, in the calculation I skipped, we used several times Osborne conjecture just to prove some identities between Euler characteristics of homologies. For example, when you change the system of positive roots, because the character formulas are the same on compact Cartan, and we get some identities, but we can, using some tricks from homological algebra, we can actually do this in using completely algebraic methods. Okay, I think I just went too fast through my slides. So now, if you look at the statement of Osborne conjecture, which is here, and the statement we proved, then you see that using these two formula, you can establish the equality between the homological pairing and the elliptic pairing between the character of those representations. Finally, if we apply this formula to discrete series, then we can prove that the higher x between discrete series representations vanish. Therefore, our homological pairing becomes just equal to the multiplicity pairing, and this recovers the original result of Harishchandra. And I want to point out that everything we use in this argument is relatively basic, and it doesn't involve any subtle results about discrete series, about representations. We just use the classification of irreducible Harishchandra sheaves and the connection with standard Harishchandra sheaves, and we use the duality theorem to identify the global sections and see that the modules appearing in our calculation are generating the K group. Okay, so finished early. Any questions?
you conclude this higher vanishing of X groups?
I mean, this is. Well, how does show this vanishing? I think this is David's result. I mean, Zuckerman, yeah. I mean, our argument is using the identification of discrete series with global sections of standard Harishchandra sheaves attached to the closed orbits, what I discussed in the workshop lectures. We use this, and some information you get from this to get this vanishing. I can send you proof with some calculation, which is few lines long. I mean, Zuckerman probably used cohomological induction, what is, I am sure, formally completely equivalent to this. Yes, yes, you can do that, yes, too.
I was saying, okay, if you use the dictionary between the
modules and
sheaves on, I suppose, curve B or something like that, then this becomes a standard computation in
Yeah,
PGA, basically, for diagrams.
yeah, yeah.
Is equivalent to some equation algebraic geometry?
I mean, you can do this, yes, yes. I mean, if the discrete series different, different discrete series, they have, as Arvind pointed out, the supports are disjoint. So, but you have to have a right dictionary in homological algebra, because the taking equivalence of categories gives connects you with X in the category of U theta K modules, and this is these are GK modules. So I think there is still some trick needed.
Can I ask, is this same statement known, is this what Roman proved for discrete series in the other case?
Yes, this is exactly the same statement, because, but the proof is totally different, of course.
Doesn't like D modules.
Yes, but even conceptually, he uses this Bernstein resolution, which Bernstein used in his notes to prove this. So, I mean, although one would expect that there is some kind of formal analogy, like Harishchandra's Lefschetz principle, we were looking in this, we couldn't figure out any similarity. So I never talked to Roman about this, but definitely Schneider claimed that there is no analogy. I mean, in a way, I mean, my attachment to result is more or less of aesthetic. I like that there is a clean statement which holds in general, but to be honest, I don't know exactly what to do with it. I'm sorry that I didn't give a slide talk for ages, so I went through slides too fast.
Other questions?
mean, this works in all the cases. So there is no restriction on lambda.
So you don't have to have a displacement.
No, I mean, again, this is one thing I skipped. I went too fast at this point when I was discussing the generators of the category. I said that you take category of the lambda modules for lambda antidominants. So if lambda is regular, global sections give you all standard Harishchandra modules, and taking global sections of irreducible gives you all global sections of irreducibles. But if your infinitesimal character is singular, then the category of Harishchandra modules is a quotient of category of D modules. So the D module generators give you the generators there, so the singular infinitesimal character is covered, yes. Oh, no, I mean, in general, there will be higher X. Yeah, because they look at discrete series and say some finite dimensional thing. Yeah. Yeah.
Okay, other questions? Okay, if not, let's. So we have a longer break, so we'll come back at 4.